be talking about today, but also on some other topics like quantum dynamics, quantum information. But I believe Rui's favorite topic is still a topic related to topological holography, which is the one he's presenting today. And let's welcome. Please go ahead.
Okay, thanks for the wonderful introduction. And it is my great pleasure to give this talk. So topic is Gapless SPT and topological holography based on these three papers. So the first one was by me and my supervisor, Drew Porter, and the last two are just me. So before we start, so I want to discuss a little background history. So this concept, Gapless SPT, Gapless symmetry-protected topological phases, was first introduced in this work by Thomas Gaffetti, Daniel Parker, and Roman Vassar. Are certain Gapless systems with symmetry that exhibit topological features such as edge modes. And so intrinsically, Gapless SPTs, also called gSPTs, were introduced by Ryan Sorgen, Ashman Vishwanath, and Ruben Versen. So they are Gapless SPTs with emergent anomalies. So the topological holography or SymTFT or SymTO paradigm aims at providing a unified framework for understanding gaps and gapless phases with symmetries. So then a very natural question is how do we incorporate Gapless SPT into SymTFT? So progress was first made so in this work by me and Drew Porter, and also by this work by Shenjie Huang and Meng Cheng, where it was found that the 1+1D G-Gapless SPTs correspond 1-to-1 to condensable algebras in the 2+1D G-gauge theory. So writing here as the vector. So this correspondence has been generalized to non-invertible symmetries and fermionic cases on higher dimensions. So here are some recent ones. So this is one by Laksha, Gai Yuhan, Huang Zhenjie, and some collaborators. So focusing on 2+1D Gapless SPTs, and there is also a very recent one by Omer and Xianggang on 1+1D that discussed 1+1D non-invertible Gapless SPTs. Okay, so the folklore in this field is that say Gapless SPT, so say here can be some generalized symmetry, correspond to a condensable algebra in the SymTFT, they say. So there are some obvious questions. So what is a Gapless SPT exactly? And so a related or more refined question is that when we say classification of Gapless SPT, what are we classifying exactly? So assume we can answer these two questions. So basically means that the one side of this correspondence is understood, right? That we can classify them. And if we can also classify condensable algebras, then can we prove this thesis rigorously? So I write this as a thesis because as of yet, so it's like it's a very vague thing, right? It's not vigorous. So I will try to answer these questions in this talk. And throughout this talk, D is based on dimension. Okay, so here's the outline of this talk. So I will give a working definition of G-Gapless SPTs. So G means that I will only be focused on like systems with invertible symmetries. I'll briefly discuss non-invertible generalization near the end of this talk. So this is a definition that allows us to classify and construct lattice models of G-Gapless SPTs based on the decorated domain wall construction. And with this definition, so you can have like different definitions of Gapless SPTs, but so with this definition, I can prove a lambda sequence connecting G-Gapless SPT and gSPTs in all dimensions. And this will allow us to compute Gapless SPT, like the classification of Gapless SPTs. So I would explain what this symbol means later. So the point is that, so I want to argue that this is a definition that fits into the SymTFT paradigm, right? So you can have other definitions, but if you want a perfect like agreement, with the bulk, then this is the correct definition. So in 1+1D, there is already an existing classification of G-Gapless SPT based on the symmetry fractionalization principles. I will review this approach and show that it is actually equivalent to the decorated domain approach. And by analyzing condensable algebras in the 2+1D and 3+1D G-gauge theory, I will prove the thesis for D equals 2 and 3. And if I have time, I'll briefly discuss how the proof can be generalized to higher dimensions. Okay, so let me start by discussing some general structures of Gapless SPT. So roughly speaking, so this is this is not a rigorous definition. So a Gapless SPT is a system with symmetry G, where not all G charges are gapped. So some are gapless. So whether a G charge is gapped or gapless is controlled by a normal subgroup, such that the gapless charges are those transforming trivially under N, and the gap charges are those transforming non-trivially under N. So in other words, all the gapless charges they form the fusion subcategory rep of G more N. So these are basically the charges of G such that N acts trivially, right? So they form a fusion subcategory. So this leads to the following terminologies. So N is called the gap symmetry, right? So it acts on the non-trivial, it acts non-trivially on the gap charges, and G more N is called the IR symmetry. It is the effective symmetry of the gapless charges. And we call a G gapless SPT a Gn gapless SPT if its gap symmetry is N. So a very interesting example is, for example, a G-SPT is a Gapless SPT. And so this sounds like a bad terminology, but later, so I will give a classification of Gn Gapless SPT, and if you take N to be G, you get cohomology. Okay, you get the gSPT classification. So this is actually very nice. So let's look at some examples. So the first example is a critical cluster chain. So basically, start with this cluster chain, which has Z2 times Z2 symmetry, and I label them by Z2A and Z2B. Right? Here are the symmetry generators. And let's try to break the Z2A symmetry by adding this ferromagnet term. So for some critical value of this coefficient, which is actually 1, the system will be symmetric and gapless. Right? So, and you should expect this to be just icing. Right, this is like symmetry, Z2 symmetry breaking. But the point is that Z2B stays gapped, right? So like this term does not affect the tau spins at all. So this is still identically 0. So Z2B stays gapped. So so the Hamiltonian at the critical point is a gapless SPT, right? So by our definition, this is Z2 squared Z2 gapless SPT. And so let V be the SPT entangler that exchanges the cluster state and the trivial paramagnet state. Right? This is a finite depth local unitary, symmetric under Z2 squared. And then if you conjugate with this SPT entangler, you get this Hamiltonian, which is just, so you can say the last two term is just critical icing, and the first term is some decoupled paramagnet, right? So this is just icing plus something trivial, and V is FDLU, which means the critical point is just icing CFT. So what is non-trivial about this icing critical point?
Question.
Yeah,
you
go ahead.
Just to make sure, in your definition of, can you go back to the definition for Gn Gapless SPT?
Yes.
So in this definition, you still require something to be gapped. Basically, I want to clarify what is not a gapless SPT by this definition.
What is not a gapless SPT?
If everything is gapless, then you don't call it gapless SPT, right?
Oh, I think we still call that gapless SPT. That would be like G1 if you take N to be the trivial group. Like all the charges are gapless. If all the charges are gapless, like if you have just Z2 and it's critical icing, then it's still gapless SPT. So the point is, so I guess is like, are there non-trivial gapless SPT? You can see in that case it's trivial gapless SPT.
So in your definition, is it correct that everything is gapless SPT?
Yes, as long as it's symmetric. Actually, so I think I need to also impose this condition, because I cannot provide a proof that this is always true. That is, the gapless charges always form a fusion subcategory. It could be that it's not closed under fusion, something. So I do require this structure that there is a normal subgroup that controls whether a charge is gapped or gapless. Yeah.
Mm-hmm.
Yeah. So I guess so in this definition, so like just like say icing CFT with Z2 symmetry can be called a gapless SPT. And so this is not a very rigorous definition, because we definitely want a good definition is something like a system and more out some equivalence relation, right, like SPT. So we do not have that structure here yet. So this is just like to give you like a general idea of what we are looking at.
Mm-hmm. So I think you just said it's possible that I have a system with G symmetry, and there's a gapless sector and the gapped sector. The gapped sector transforms non-trivially under some subgroup. You said it's possible that this subgroup is not a normal subgroup?
I think maybe I can say, like, so we have some gapless charges, but they may not form a fusion subcategory of RepG. Yeah.
In what case will that happen?
So okay, if I have two gapless charges and I fuse them and it becomes gapped, I don't know if this is possible, but so in my mind this seems impossible. But if that is possible, then we do not have this structure. So I only consider the case where if you have two gapless charges and you fuse them, it stays gapless. Yeah, and it's actually more refined. This is a fusion subcategory, which means like there's some requirement on the morphisms as well. So it's not just objects.
Okay, thanks.
Okay. Okay, so I think I'm here. So yeah, so what is non-trivial about, so so the critical point is SymTFT. So what is non-trivial about this critical point that we want to call this a gapless SPT, a non-trivial one, right? So notice that the usual disorder operator vanishes, right? If you just take the like this is like a domain wall of the Z2A, I believe, right? It's actually 0 because the first term commutes with the rest, right? So the first term is 1. So the first term contains this in the ground space. The first term is 1. So the first term contains this sigma z, so which anti-commute with this. So just take one that's like at the endpoint of this string, right, and then do the commutation. So you see this is 0. But actually, so instead the decorated version behaves correctly. So if you put some tau this string on the edge of this string, this will behave like the correct disorder operator in the SymTFT. And so this result just follows from applying the entangled way to the disorder operator in the standard IC model. So basically here, right, we know the behavior of the disorder operator, then just apply V. So it actually changes. It changes to this guy, right? So it's decorated by these tau these things. Okay, so when they say that, so the Z2A domain walls are actually decorated with Z2B charges. And so this actually leads to something, I would say, observable. This leads to tuple grounds generality on an open chain, which is sometimes called the edge modes of the Gapless SPT. So this is what's non-trivial about this system, right? So if you have this system, there's no edge modes, right? Okay, so to see the full picture and to make connection with SymTFT, let's just consider all the symmetry defects, right? Charges and domain walls and their combination, basically. So the Z2A charges are the sigma Z strings, let's call them GA, and we have Z2B charges, the tau Z, and we call them EB, and the Z2A domain wall operators like this, it creates a pair of domain walls, I call them MA, and this creates a pair of Z2B domain walls, it's called them MB, and their combinations, which means their products. So let's say a defect is condensed if its correlation function turns to a positive constant. And we say it's confined if its correlation function decays exponentially. And we say it's deconfined if its correlation function decays algebraically. Right. So for now, this is just definition, but of course, this matches with our usual concept of being condensed. Right. It's like a correlation function. If it's a positive constant, that means the charge is condensed. Okay. Then if we look at this system, we see that in the ground state, as I just said, so the first term commutes with the rest. So this is just 1. And if you just take product of this term, we get a string of tau x decorated with sigma z, and this is 1. So, and this is M, so in the middle, this is MA, and this is MB, and this is EA. So this actually shows MBEA is condensed. And so these two correlation functions that we just discussed can be interpreted as MA is confined and MAEB is deconfined. So in the usual in the usual SymTFT, this will actually be deconfined, right? So but in this gapless SPT system, this is confined, and the decorated version is deconfined. And this matches perfectly with condensation, MBEA in the 2+1D topological order. This is the 2 square gauge theory, 2+1D. So if you call this, if you like, this is M is a flux, E is a charge, right? And then if you condense MBEA, this is what will happen, right? If you condense MBEA, then, for example, MA will be confined and MAEB will be deconfined, right? Okay, on the other hand, this trivial model, right? This is just like SymTFT with some decoupled tau. This is described by, so we have tau being 1 and tau x is 1, tau z is 0. So MB is condensed and EB is confined. And this is now this is a usual disorder operator. And also the charge correlation function is the same, it's self-dual. So MAEA are deconfined. So this matches with condensing MB in the 2+1D topological order. Okay, so now we've made connection to something that's 2+1D, right? Okay, so here's the conclusion. So the symmetry defects of a 1+1D Z2A times Z2B symmetric system are labeled by objects in the 2+1D topological order. And this is called the symmetry topological field theory, symmetry topological order of the symmetry Z2 squared. And the structure of symmetry defects in this trivial system, sorry, this is the equal sum is missing here. So it's fully captured by the condensation 1 plus MB in the SymTFT. And the structure of symmetry defects in this gapless SPT is fully captured by the condensation 1 plus MBEA in this SymTFT. You can see that it's kind of like twisted, right? MB is like a boring one, but now we have this charge attached, so that's what makes it non-trivial. Okay, so
excuse me.
Yeah, go ahead.
So could you please go back? Yeah. So what do you mean by condensing MBEA? So in my mind, I think it looks like the fermion in the toric code. Is that the case?
Oh, yeah, this is not fermion because A and B are like different they live in different Z2 sectors. There are two, if it's like M times Z, it would be a fermion, but this is like M in one Z2 and this E in another Z2. So they break trivially. So this is still a boson. Does that make sense?
So it looks like a double layer Z2
Yes.
case theory.
Yeah. Yes,
So that's
exactly.
a double layer of toric.
Yes, two copies of
I
toric
see.
code, and
I
M
see.
in one layer and E in another layer. So they would break trivially.
Okay, thank you.
Yeah. Okay, so usually people like to draw this sandwich picture, right? So basically, all the structures I discussed can be fully captured by this so-called sandwich picture. So okay, so the SymTFT is the two square gauge theory here on the right, right? And so the middle domain wall condenses MBEA. So we do a condensation here, actually to like in the entire left region, to the left of the domain wall, including the domain wall itself, we condense MBEA. Then the left patch is the Z2 gauge theory generated by the deconfined anions MAEB and EA, right? So this is in red, right? Because this is like, you see, like this flux is actually like kind of like decorated with a charge. So this MAEB will generate the IR-Z2A symmetry. Okay, so basically the SymTFT idea is that you start with the sandwich, right? So with this domain wall in the middle, and so the left is just ISymTFT, and you just do the compactification, right? Dimension reduction, so it becomes a 1+1D system with the two square symmetry. But the gapless degree freedom, that is this ISymTFT, actually only transforms faithfully under this Z2 symmetry. But this Z2 symmetry is, is like MAEB. It's not just MA, so that's what makes it non-trivial. Okay. So another example is the Z4 gSPT. So basically we have two spins per unit cell, and this is Hamiltonian. So this is called the Z4 intrinsically Gapless SPT. So the detailed analysis can be found in this paper. It's a very nice paper that derived everything. So by Li Linghao and Masaki and Yunqing. So you can find all the details there. So there is an on-site Z4 symmetry, right? So you can check this as Z4. This is order 4. The U square is product of tau x. So and this model is FDLU, finite depth local unitary equivalent to the following. And so this is actually just Levengood Hamiltonian plus trivial, because you say in the ground, so this tau x commutes with the rest, which means in the ground state, you can set this to 1. And once this is set to 1, this is 1 and this is 1. So you just like sigma x minus sigma z, sigma x, sigma z. That is a standard Levengood Hamiltonian. So it's gapless and it has anomaly. So this is exactly solvable. Which means this model is also exactly solvable. You just apply this FDLU. And specifically, the IR theory is a compact boson. Okay, let's look at this. So the last term commutes with the rest, right? This just follows from like here, like this last term commutes with the rest. So the last term commutes with the rest. And if you do a similar analysis as we did before, so this is like m squared times e squared, right? So this tau x, as I explained, right? So it's like tau x is like u squared, right? So which means it's like m squared. And this sigma z is actually a double charge, right? Because you can check, for example, it anti-commutes with u, right? Which means like it's charged like it's 1, it's not I, right? Under Z4. So basically, this last term is 1 in the ground space, and this can be interpreted as E squared M squared is condensed. Okay, and you can check the UU domain where this is again confined, right? If you just take the symmetry generator and just truncate it to a finite interval, it's 0. Again, this is simple because okay, in the ground space this is 1, and this contains the sigma z, and there is a sigma x here, so they would anti-commute. So just take 1 on the boundary of this term of this string, they would anti-commute, and this is 1, which means this is 0, meaning M is confined. Okay, because this is just symmetry generator truncated to it's like inserting a flux, so the flux is confined. But the decorated version is deconfined, right? It's decorated with this tau z. So you can check this means that E times M is deconfined. Again, so basically the flux has to be decorated with a charge in order to be deconfined. And so now this structure matches with the condensation E squared M squared in the 2+1 Z4 gauge theory. If you just call E a charge, M a flux, and if you condense E squared M squared, this is what you get. If you condense E squared M squared in this 2+1D Z4 toric code, the M would be confined because the M breathes non-trivially with the E squared here, and the EM is deconfined because it breathes trivially with E squared M squared. Right. Okay, now we can do this sandwich picture again. So now we start with this SymTFT, which is a 4 gauge theory, and we condense E squared M squared. Right. on this domain wall and also to the left of the domain wall. And the reduced theory, so the condensed phase, so by which I mean, what do you get after condensing M squared, is generated by the deconfined anions, which is EM, E times M, and E squared, which is a twisted Z2 gauge theory. And this is very interesting. So the IR symmetry generator is not E times M, right? As we saw before, like the deconfined flux is actually like E times M, right? So symmetry generator is E times M, and this is a fermion. This is not a boson. So this indicates the IR Z2 symmetry is anomalous. And indeed, so if you start with symmetry generator, and you can say that, so in the ground space, this is 1, which means you can replace tau x with product of sigma z. So we do that, we replace tau x with product of sigma z. We get this, and this is anomalous. This is a standard, anomalous Z2 action on the Levengood Hamiltonian. Yeah. Okay, so this is why it's called IGSPT. It's intrinsically Gapless SPT because it has this emergent anomaly, right? So this IR symmetry is actually anomalous Z2. And in the SymTFT, it manifests as this twist of this condensed phase, right? This condensation makes the condensed phase a twisted Z2 gauge theory. And this twist is what it matches with the anomaly of this 1 + 1D system. Okay, so let's summarize what we just discussed. So what does the SymTFT say? So it determines the topological properties of symmetry defects, like whether it is condensed or confined or deconfined, and their fusion rules, etc. But what does the SymTFT not say? I think this is very important because there have been a lot of discussion on this. So in my view, so it does not determine any non-topological information, like critical exponents of deconfined defects, right? It tells you what is deconfined, but okay, it's deconfined. What's the critical exponents? You don't know. Okay, so in light of this, let's just give this following definition, which is a little bit better than what we just gave before. So let's say two G symmetric systems are G equivalent if they have identical topological properties of G defects. Right? By G defects, I mean like the G charges and G domain walls and their combination. Right? And we say a G-Gapless SPT class is an equivalent class of G symmetric systems under the above equivalence relation. Okay. So here are there are still some problems. So the first is that topological properties is a vague term, right? What do you mean by topological properties? Probably just this, right? What is condensed, what is confined, what is deconfined, and their fusion rule. That's probably what we mean by topological properties. And in 2 + 1D and higher, there can be topological defects not associated with symmetry. So we should probably consider G-Gapless symmetry enriched topological order. So this is very weird, but this is definitely some possibility we should consider. And I will address this soon. And so our example suggests that these topological properties of symmetry defects are captured by the decorated domain wall construction, right? As we've seen in the previous two examples, you can basically summarize the whole thing by saying that, some charge is decorated on some domain wall, and that's it. So let's just try to do that, like in a general case. Okay, so this is a general theory of decorated domain wall. So it's a method of constructing complicated SPTs from simpler ones. So it starts by breaking the symmetry group into a group extension. So we have a symmetry group G, and if we can write this as an extension of G over N by N, then we can obtain a gSPT phase from the following procedure. We start with the G mod N broken and N paramagnetic phase, and we put some N SPTs on G over N defects, which include domain walls and domain walls between domain walls, etc. Right? Like defects of all possible codimensions. And then we proliferate the G over N defects to try to restore the symmetry. Right? But this may not always succeed. So this procedure only yields a gSPT if some consistency conditions are met. Okay. So to be more precise, so the N SPT decoration on a p-codimensional G over N defect is given by a function. Right, so this basically is because it's like p codimension, right? So it requires like p values of G over N, and so it's decorated with some SPT. So this symbol, this H D minus p of N, is the classification of N SPTs in D minus p dimension, right? So this decoration is given by some function in this group, some element of this group, and so the consistency conditions look like this, right? So yeah, I will explain what do you mean? So, and this delta I are linear maps called differentials. So in total, there will be D minus 2 conditions, and they can be divided into two groups. So the first D minus 1, make sure there's no N anomaly on G more N defects. Right, we don't want N anomaly. So that N will stay gapped and symmetric after proliferating the G over N defects. And the last one, as you can see, actually takes value in this, the d plus 1 of G over N. So this is the classification of anomaly of G over N in D dimension, right? So requiring this to be 1 means that we want there to be no G more N anomaly, right? So that the full symmetry G becomes gapped and symmetric after proliferating the G over N defects. Okay. So for gapless SPT, we make the following crucial changes. So the first is that the last condition is dropped because G over N is no longer gapped. We don't want it. We don't need this to be gapped, and this is gapless, and it can be anomalous, right? So this condition is like G more N is not anomalous, but now it can be anomalous. So we drop this last condition. So for example, in 1 plus 1D, if we take N to be Z2 and G over N to be Z2 with a non-trivial extension, so the whole group is Z4. Then if we take a non-trivial F1, so if we only have F1, it turns out it's actually in this group. It's like it's a cocycle, and this group is Z2. So and if we take the non-trivial element, and then you can check that this last condition is violated, right? So it's a non-trivial element in the non-trivial 3 cocycle of Z2. And so this describes the Z4 gSPT that we just discussed before. So the Z2 G over N domain wall is decorated with Z2 N charges, and this results in a non-trivial emergent anomaly. Right, so this shows that for gapless SPT, we definitely do not want this condition. Okay, so another thing is that this FD term, which is like a D cochain of G over N, is a phase associated with an insertion of a mesh of G over N defects, right? But now since G over N is gapless, this is no longer well defined. So here's an example. So if we take N to be trivial group, as we just discussed, like this is definitely possible, right? Then this means all of G is gapless. So in this case, you can check that the FD is actually the only non-trivial thing left, and it's a cocycle of G, right? But for SPT, it's totally fine. For SPT, like there's no decoration, right? We're not doing any decoration. This N is trivial. We just need a D cocycle of G to define gSPT. But if the G is gapless, then this should not play any role, right? Okay, if we, for example, if we start with the cluster chain and we make the entire Z2A times Z2B critical, then the critical theory cannot be distinguished from the usual typical critical icing in any way. Their symmetry defects would behave identically. So in the previous example, only like Z2A or Z2B is critical. But if we make the entire Z2A times Z2B critical, it should be regarded as a trivial gapless SPT, right? So in this case, it's like this term should not be regarded as part of the information, part of the data, right? So more generally, if we start with any gSPT and we make G critical, we should expect this to be a trivial gapless SPT, no matter what gSPT you start with, right? The result should be regarded as trivial. Okay, so the usual decorated domain wall theory for gapless for gSPT for ordinary SPT in 1 plus 1D looks like this on the E0 page of the spectrum sequence. So basically, we have 3 data. We have 3 functions: F0, F1, F2, and 4 equations, right? Remember, we have D plus 2 equations. We should have 4 equations. So these are labeled by 4 colors. Like this one means like basically, so F0 should give you something 0 here. And this blue equation means that so this place will actually receive a contribution from both F0 and F1. So together they should give you 0. And here, this place will receive contribution from 3 terms, and together it should be 0, and similarly here. And so basically, if we take these 3 functions that start, so basically this is like cocycles, and so coboundaries or like trivial SPTs would be, functions F0, F1, F2, such that they come from some little f and little g in this way, right? So basically, if you take F0, F1, F2, such that the left diagram is satisfied, you mod out F1, F0, F1, F2, such that there exists Fg, little f, little g, such that right diagram looks like this. Then you get the usual, actually, this should be H2. This should be H2, H2 of G. You get SPT classification, right? So here are some physical interpretation of this data, right? I have 3 pieces of data. So F0 So it's always a Q cocycle of n. So this is just SPT class of n, right? And if there's if F0 is there, if F0 is trivial, then this F1 data describes the charge on the G over n domain walls. And this is like a decorated domain wall data here. If both are trivial, then we are left with the last F2, and this just describes the SPT of G over n. And so yeah, the three of them, all three of them can contribute to the final SPT class of G. Okay, then the decorated domain wall theory for gapless SPT in 1+1 would look like something like this. So again, we can think of this as some cocycles model out some co-boundaries. But the cocycles look like this. We only have two terms, F0 and F1, and we don't have this last, the red equation is gone. I won't have three equations. The red equation is like the emergent anomaly, like the anomaly of G over n thing, right? So if we take F0 and F1, satisfying the left diagram, we model out F0, F1 that comes from some F, like as in the right diagram. This should be the classification of Gapless SPT. And so I use this notation to denote the classification of Gn Gapless SPT in two space-time dimensions. Right. So for example, this F0 is still two cocycle of n. So this is just the SPT class of the gap sector, right? So in a Gapless SPT, we have a gap sector. The gap sector has symmetry n, and so you can talk about the SPT class of the gap sector. And this F1 is, it's like a function that depends on one element of G over n and one element of n. This is n charge on the G mod n domain walls. So technically, this is only correct when F0 is 0. When F0 is trivial, then you can interpret this as the n charge on the G mod n domain walls. In general, it is a torsor over n charges. So basically, you say the gapless SPT is some sort of cohomology, right? Some sort of cocycles, model coboundaries. So how do we compute this? So to compute this, I prove a non-exact sequence. So the first thing we can do is that we can take the emergent anomaly, right? Start with these two terms. We compute its contribution here. This is no longer 0. Well, we remove this condition. So we just get something in the H3 of G over n. So this defines a map from the classification of Gapless SPT to SPT of G over n in three dimension, which is the same as anomaly in 2 dimension, right? And more explicitly, so F0, F1 goes to this expression and take the cohomology class. Okay, and from spectrum sequence, we know that a term here is trivialized. So this is in G over n, right? So it's trivialized in G if and only if it's hit by some F0 and F1 in this way. So basically, this means that when you compute this anomaly, you don't get everything. You don't get all the terms in this group, right? You're only going to get the terms that are trivialized in G. So this just means this sequence is exact. Okay, so start with the gapless SPT, we can compute this anomaly. But this anomaly, when the image of this O is the kernel of this P star, which means that the anomaly is always trivialized in G. The physics is that the anomaly of a gapless SPT is emergent. It always trivializes when put back to G, right? Like in the Z4 gSPT example, right? This emergent Z2 anomaly trivializes in Z4. Okay, so we call our first example. So we started with a cluster chain and we tune that to a critical point, and we get a non-trivial gapless SPT. So now we generalize. So start with the gSPT, which I interpreted as 3 functions satisfying 4 equations, right? Now we just ignore F2. We just get rid of F2. We have F0 and F1. It satisfies the first 3 equations, and that's good enough. So we obtain a gapless SPT F0, F1, right? And the physics is that we're making G more n gapless. So this F2, as we discussed before, is no longer well defined. We just ignore that. So this procedure defines the map from the class from SPT of G to gapless SPT of Gn. So for example, the cluster chain goes to the critical cluster chain, right? Okay, the claim is that we have this exact sequence. Okay, so this means that a gapless SPT has no anomaly if and only if it comes from an SPT. Okay, so this is a mathematical proof. You can check. But let's just talk about the physics. So the image of R, right? The image of R, so as we discussed, if you start with SPT, you make G over n gapless, you get a gapless SPT. So But these gapless SPT are called weak ones, like the critical cluster chain. They're obtained by making G over N gapless in a gSPT. So then we can undo this. We can ungapless G over N to return to the gSPT, right? So this shows the weak gapless SPTs have no emergent anomaly. And this is clearly an if and only. You can run the arguments backwards, right? So that means this is exact, right? So it has no anomaly.
Question.
Yes.
Can you remind me, in the definition of gapless SPT, at which stage you require that G itself has no anomaly?
Okay, so maybe we should say, so a G gapless SPT is first of all system with a on-site G symmetry.
Okay,
Like
that's
yeah. We start like G symmetry itself is not anomalous. It's I think it's part of the definition of
what was this stated in the definition previously?
Okay.
Somehow.
I think it's not in this definition. Yeah, it's not in this definition, but somehow
Okay.
in the decorative domain or construction,
you impose it.
Yeah. I think it's built into this definition here. So basically, these two conditions. Yeah, because if you only drop the last condition, then this is no longer one. It's something, but it's always something that's trivialized in G. So I don't think this can describe something with G anomaly. If the G itself is anomalous, then it's beyond the description of decorative domain or construction, at least.
And you don't, in that case, you don't call it gapless SPT.
Yeah, I thought about like defining something like anomalous gapless SPT, but I don't have anything solid to talk about right now. But I think it's definitely something you can define. Like, okay, one example. I can give you right now one example. Okay, consider a two-dimensional 2+1D SPT. Then the boundary will have anomaly, right? If the gSPT in the box or in a disk, the boundary will have G anomaly. So usually we say that if the boundary is symmetric, it must be gapless. But actually, it can be not entirely gapless. Like it can be a gapless SPT.
We're considering an anomalous 2D SET.
No. So you consider a 2+1D SPT of G. On the boundary, there will be G anomaly, right? And boundary is 1D. Boundary is 1D with anomaly G.
Yeah.
With anomalous G. So usually we say, well, if it's symmetric, it must be gapless, right? Like in the Levengood model, with the boundary, if it's gapless, if it's symmetric, it must be gapless because this is 1D. There is no topological order, right? It must be gapless if it's symmetric, but it does not have to be fully gapless. If you okay, by which I mean that there can be a like N that acts on some of the G charges on the boundary can still be gapped. Yeah. So this would be something like a anomalous gapless SPT.
Okay.
It lives on the boundary of an SPT, but it is not fully gapless. Some charges are gapped. Yeah, I think this is something that maybe we can explore in the future. But right now, I'm only looking at cases where G is not anomalous.
But in that case, do you think the decorative domain picture can be modified to capture it?
I think so. Yeah. But yeah, but I don't know. I don't have anything like rigorous to say right now. But I think some generalization of it should work.
Thanks.
Okay. So I think I was I was here. Oh wait. Oh yeah, here. So those gapless SPTs that are obtained by making an SPT critical are called weak, and they don't have emergent anomaly. And this is if and only if it has no emergent anomaly, you can just open the G over N gap. without introducing topological order, without breaking the symmetry, which means it is in the image of R. So, okay, so this is exact. Finally, we can examine the kernel of R, right? The kernel of R. So, okay, if something is in the kernel of R, right? So SPT, which again I write as a triple F0, F1, F2, and so R basically just ignores the last term. So if this is 0, this basically means that the first two terms are trivial, which means this only has a contribution from the last term. And the last term is when this happens, when it only has a contribution from the last term, this last term will be a two-quotients of G over N. So this means anything in the kernel of R actually comes from some G over N SPT, right? So it's a gSPT, but it comes from the pullback of a G over N SPT. So this is exact. The physics is this. So if a gSPT comes from a G over N SPT, and then when we make G over N gapless, the behavior of its symmetry defects can no longer be distinguished from that of a trivial Gapless SPT, right? Because like it comes from, okay. Anyway, sorry. So for example, if we take N to be the trivial subgroup, right, then this is identity, right? Like if N is trivial subgroup, this is G, this is also G, this is identity. So R is now 0 map. This means all SPTs become trivial if the entire G is gapless, right? If the entire G becomes gapless, then all SPTs become the same thing. You cannot tell the difference, right? Like this is just what we discussed earlier. If you start with the cluster chain and you make Z2 square critical, then it's just the same as a trivial power magnet then tuned to the Z2 square critical point, right? Okay. Okay, so put together we have the exact sequence like this. The gSPT is sitting in the middle. This is taking anomaly. This is like weak. This is like a weak Gapless SPT. Okay, and this discussion is not limited to 1 plus 1D. It works in any dimension. And so we have actually a non-exact sequence like this. Yeah. Okay, so from this non-exact sequence, we can deduce the classification of Gapless SPT as a set. Right, so generally, this is not an inequality as a group, but as a set, we have this. So it's basically kernel of this times SPT-G quotient image of this. Okay, let me explain this. So first of all, this is good because the problem reduces to ordinary group cohomology calculation, right? And you can compute this now. It's all like computable. And so the first factor is just the emergent anomaly of the Gapless SPT, right? For anything here, you can first compute this emergent anomaly. That gives you this first term here. But if you fix the emergent anomaly, right, you fix an image here, the different elements are related by image of this guy, right? So this just means that for a fixed emergent anomaly, different Gn Gapless SPTs are related by stacking with gSPTs, right? But not all such stacking operation is non-trivial. So in particular, stacking a G over an SPT does not change the Gapless SPT class. So Gapless SPTs with a fixed emergent anomaly is a tosser over gSPTs over G more N SPTs. So okay, here is an interesting thing. So if you take N to be G, so everything is gapped. Then so okay, if N is G, so if N is G, this is 0. So then all the pullback maps are 0. So if pullback map is 0, so this is trivial and this is immediately trivial. So the GG Gapless SPT is just the same thing as gSPT. So you can say SPT is a special kind of Gapless SPT, at least in terms of the classification. Okay, here are some classification results. Yeah, you can do the group cohomology calculation. This is just to show that it's computable. Okay, so I don't have much time now, so I do want to cover this last part. That is very important because this is relationship to SymTFT. So 1 plus 1D Gn Gapless SPTs were classified by a different method in one of my earlier works. So let's recall that how you can derive the H2 classification of 1 plus 1D gSPTs. So let UG be the symmetry generator. In the ground space, this effectively acts on the boundary. Right? This is sometimes called symmetry fractionalization. So UG reduces to some operator on the left, some operator on the right endpoint. Of course, we're talking about the finite chain. So for UG to form a linear representation, for example, the left one only needs to form a projective rep, and this gives you the H2 classification. So for a 1 + 1D Gn gapless SPT, we can do the following. So n is still gapped, right? So we can still do the symmetry fractionalization for Un. And so Un will form a projective representation of n, so given by some 2 cocycle of n. So we have this trivial identity, which is that if you conjugate Un with Ug, you get U of G conjugate n conjugated by G. This is trivial. But then when we strip this Un to one of the endpoint, like say the left one, this only needs to be satisfied by up to a phase, right? And the right one can give you the complex conjugate of this phase, and this will be satisfied. Okay, now we have 2 phase factors, eta and epsilon. So there are some natural associativity conditions these 2 symbols need to satisfy. So this is a result of this work. So 1 + 1D Gn gapless SPT is classified by the data eta and epsilon, satisfying these 4 equations. A major result of this work is the observation that condensable algebras in the 2 + 1D G-gauge theory have exactly the same classification. So yeah, so condensable algebras in this theory have been classified by mathematicians. You just look at the paper and you see exactly the same 4 equations. Okay, so this classification looks a bit messy, but it's actually the same as a decorated domain theory. So okay, I'm running out of time, so I'm just gonna say that you can do some redefinition, and turns out those equations are just the same as these equations of the spectrum sequence. And furthermore, the emergent anomaly can be computed by from these symbols using the Elson-Nyack method, and it gives this expression, which if you check is exactly delta 3 of F0 and delta 2 of F1. So yeah, this just matches with the decorated domain classification of gapless SPTs. And so if we denote this by the corresponding condensable algebra in the bulk, and if we condense this, again, mathematicians have computed what happens when you condense it. You get a twisted G over N gauge theory, and this twist is given by exactly this expression. Okay, so now let's move on to 2 + 1D with the 3 + 1. Roughly speaking, a condensable algebra in this 3 + 1D G-gauge theory has the structure of a G-cross braided fusion category, such that something. So in the sandwich picture, so this is the sandwich picture, but now this domain wall is 2 + 1D, so which means it can have its own topological order, and this domain wall can be topologically ordered. So if the domain wall has non-trivial topological order, we probably want to call the corresponding 2 + 1D system a gapless SET. Although I do not know exactly what that means, but there are anions in the system. If you just do the dimension reduction, there will be anions in the system. So probably want to call that gapless SET. So here's the definition where we don't want to have anions in this system. So a minimal condensable algebra is one that induces a trivial topological order on the domain wall. You can make this mathematically more rigorous, but this is the idea. So we expect minimal condensable algebras to correspond to gapless SPTs, and the non-minimal condensable algebras describe something like gapless SET. Okay, so a minimal condensable algebra in this theory turns out to be a G-cross braided fusion category, such that its underlying G-gridded category is vec n for some normal subgroup n. So we are seeing this structure appearing, right? So we have this normal subgroup now, and the rest of the data that is a G-cross braided fusion structure on this guy is determined by the following. We have a 3 cocycle because we want it to be fusion, so we need a 3 cocycle of n, which I call F0, and we have a morphism of 2 groups from G over n to the Bauer Picard 2 group of vec n of this fusion category. And such two group morphisms were studied in the famous ENO paper in their appendix. So it is exactly given by F1 and F2 such that these 3 equations are satisfied. Yeah. So and after you condense it, you can prove that the resulting phase is exactly a twisted G over N gauge theory, where this twist is now a 4 cocycle given by this expression. So again, the point is that we find perfect correspondence with the decorated domain wall construction classification of gapless SPTs. Okay, here is the main result and main summary of this talk. So a d-dimensional Gn gapless SPT is defined by a decorated domain wall data without the FD term and also with possible anomaly of G over N. Right, and for d equals 2 and 3, I've proven that G-dimensional gapless SPT are in 1-1 correspondence with minimal condensable algebras in the SymTFT. And the twist of the condensed phase is exactly the emergent anomaly of the dual gapless SPT. Okay, here is how this can be generalized to general dimension. So in d-dimension, the SymTFT is something like the d-1 vec G, right? So d-dimensional G-gauge theory. And a condensable algebra in this is something like a G-cross braided fusion d-2 category. So actually, what's interesting is that this actually works even for d equals 2. And a G-cross braided fusion 0 category is just a G-crossed commutative algebra, which are exactly classified by the epsilon and the eta epsilon phase factors we just discussed. And for D greater than 2, we need to introduce a concept like minimal condensable algebra. Otherwise, the condensable algebra should describe Gapless SPT. So here's an informal definition. Actually, this is formal. A minimal condensable algebra in the D-1 vec G is a G cross Brady fusion D-2 category such that its trivial component is D-2 vec. And so homotopy classification, homotopy theory of forced extension generalized to higher categories. So the proof in this paper can be generalized to show that such condensable algebras are exactly classified by the decorated domain data all the way to FD-1 with the twist of the condensed phase given by what we expect. Okay, so here's the summary. So the topological structure of symmetry defects in G-Gapless SPTs is captured by a modified decorated domain construction. And condensable algebras in the SymTFT completely capture this topological structure. But the SymTFT does not determine dynamical properties of the Gapless system, such as scaling of operators, operator product expansion, etc. And the same idea generalizes to generalized symmetries. For any fusion D-1 category, you can say that the Gapless SPT corresponds to minimal condensable algebras in the C, which describe topological properties of the symmetry defects. So what is, okay, here are some questions for future work. So what is a Gapless SET? And is anion even well defined in a Gapless system? Well, it turns out, at least from this sandwich construction, you can allow it, but just from the system itself, right? For Gapless system, can we talk about anions? And there are any lattice model realization of them, and can we classify them? And any fermionic generalization? Yeah, and that's all. Thanks for your attention.
Thank you very much for the very interesting talk, Ray. Any other questions? Regarding the question of whether anions are well-defined in Gapless systems, I certainly think it can be well-defined, right? In Gapless theories, I can still have, for example, some one-form symmetries with some non-trivial topological spin. Then this can be used to define the anions.
Yes, exactly. So I guess the problem is like how stable are them, right? Or like you need to define some sort of equivalence relation between Gapless systems so that like anions are like invariant under such equivalence relation.
I think they should be stable. The reason is because when I say they are stable, I mean they are stable under weak local perturbations. So suppose before we add any perturbation, I already have this one-form symmetry. Then now I add the weak local perturbation. Within the low energy effective field theory, the one-form symmetry just cannot be broken by any local perturbation. So the one-form symmetry is still there. Only if the perturbation is strong enough so that the original effective theory breaks down, the one-form symmetry is gone.
I see. So this has nothing to do with the system being gapped or gapless.
So I don't think it has anything to do with whether it's gapped or gapless.
Okay, this is very interesting. Yeah.
Actually, one example of this is just the K-type honeycomb lattice model with spin 1/2 moments and isotropic coupling. In that case, it's the one-form symmetry that gives some fermionic excitation in the bosonic system. In principle, one can imagine the case where the fermion is a more non-trivial anion. So that model by itself is gapless.
Yes.
But it's
there is still I see. There's still like a fermionic anion there. Okay, so actually this is very interesting. So it has only one fermionic anion. There's nothing to breed with it. Is that correct?
Yeah. So I think this breeding non-degeneracy in gapless system cannot be generalized to gapless systems.
Okay, this is actually very, very interesting because that's exactly what you say from the SymTFT. Because you kind of if you just do this like naive generalization, you can get a concept of like gapless topological order, I guess you can say. And what's weird is that they are just breeding fusion categories. They don't need to be non-degenerate. That's something that confused me because it seems to suggest that in a gapless system, the breeding can be degenerate. And I think from your example, this is definitely the case.
I think it's possible, yeah.
Okay. Yeah, okay, that sounds interesting to look at.
Okay, any other questions?
Can I ask a question about the minimal condensable algebra? So, what is the mathematical characterization of this minimal condition?
Okay, so actually, I don't. So at least in this case, when the bulk is a G-gauge theory, the definition is just that so the condensed algebra is always G-graded, and it just demands the trivial component to be trivial, to be vague, or to be unvague in general case.
So you mean that the minimal condition just means that the trivial sector of this G-graded braided fusion category is just trivial?
Yes.
Oh, okay. Thank you.
No worries.
Any other questions? Okay, if not, let's conclude this seminar under Symmetry. And this, I want to mention this is the last seminar in the seminar series of this semester, and we will restart from the next semester. Thank you all.
Thank you very much
Thank
for
you.
the
Stop
invitation.
recording.